Thanks for joining us on this episode of Tory Story. Today, I have the honor of talking with mathematical physicist about his recent book, The Primacy of Doubt. For those of you who are interested in the fascinating study of chaos theory, or who have had the pleasure of learning from him, you might already know him as Professor Palmer, Royal Society Research Professor of Climate Physics at Oxford University. He pioneered the development of operational ensemble weather and climate forecasting, and in 2007 was formally recognized as having contributed to the Intergovernmental Panel on Climate Change and received recognition for that via the Nobel Peace Prize, along with many other scientists, including former Vice President Al Gore. So the scope of our discussion today actually covers a broad range of topics. We talk about global warming, quantum physics, what is a strange attractor, Bell's inequality, chaos theory, the universe, nonlinear systems, and everything in between. So thank you for joining me and welcome to the show, Dr. Tim Palmer.
Nice to be here. Thank you very much, Victoria.
Great. So your book is absolutely fascinating. It's so broad and encompasses so much, but unfortunately we only have an hour, more than a little over an hour, so we have to focus on specific topics. But let's begin with your going back to your early the start of your career when you had the opportunity. It was kind of a fork in the road. You had the opportunity to work with Dr. Stephen Hawking, and you decided to take the opposite direction and go in the direction of climate physics rather. So can you tell us a bit about why you decided that?
Sure. Yeah. I mean, I did start. I mean, I think I was interested in science from quite an early age, and got really fascinated with looking at the stars and reading about astronomy books and that sort of thing from quite an early age. And so I set my heart on doing, first of all, a degree in physics and mathematics, and then a PhD in Einstein's theory of general relativity, which is what I did at Oxford. That led to an opportunity to then move on to what would be called postdoctoral position in Cambridge with Stephen Hawking's group. But I think two things kind of weighed on my mind in those days. The first was that the work I did for my PhD was really very, very kind of abstract and had no kind of, no real kind of consequence for the person in the street. And it sort of did bother me a bit that, in fact, it bothered me a lot that I was going, if I took this postdoc position, I was setting myself up for a career which possibly would have had no impact whatsoever on any of my fellow humans on the planet. And that was one thing. The other thing, which is not completely independent of that, was that the kind of in fact, still to the present day, the really big problem in theoretical physics, in foundational theoretical physics, the very heart, if you like, of physics, is our inability to kind of marry together the two great theories of physics. One is general relativity, Einstein's theory of gravity, and quantum mechanics, which is the theory of atoms and elementary particles. I think probably if I had a clear idea how to do that, my misgivings about not doing anything useful for humanity might have kind of come second place. But I didn't really, and it bothered me that a lot of the problems in quantum gravity are quite kind of conceptual, almost problems. They're not ones that are going to just be tackled by doing lots of calculations. You've got to think quite hard about the nature of the problem. And at the time, I felt I didn't have any kind of obvious ideas about what direction to go. So yeah, those two things then, and a chance, I would say a chance meeting with a climate scientist, because I didn't know anything about weather and climate at all before moving. Just a chance meeting kind of convinced me that would be a good area to work in. which actually it's turned out certainly to be.
Interesting. Wow, that's really. And then later on, I mean, it turned out to be the right decision according to your book. It is. It's obviously it's groundbreaking. So there is a misconception about weather prediction. I think probably not many people really think too much about weather predictions when
No.
you. Yeah, I mean, checking the weather forecast is, nobody looks at, well, there's 80% chance of rain or 90%. I think they just see, that it's going to rain and they assume that it's going to rain. And, there's still that chance that it might not. And so it's interesting. So there's the science historian and author of Chaos, Making a New Science, James Glick, said, tiny differences in input could quickly become overwhelming differences in output. In weather, for example, this translates into what is only half jokingly known as the butterfly effect. The notion that a butterfly stirring the air today in Peking can transform storm systems next month in New York. So let's talk a little bit about what that means. And I know in your book you gave the fantastic example of Michael Fish and the Great Storm of 1987, and how this ultimately led scientists to do more, to get more accurate prediction models.
Right. Okay. Well, let's just wind back to the beginning of your question, because, that's so. Let's just wind back to the beginning of your question, because it's true that most of the time, kind of who cares what the weather's going to be like? I mean, it's not exactly life-threatening, but sometimes it is life-threatening. And if you go back to the 1970s, you can find instances of tropical cyclones that killed upwards of 100,000 people, in places like, modern day Bangladesh, because there were no warnings, and because people lived in low-lying areas, and the storm surges from the sea associated with the tropical cyclones just kind of completely came in unannounced, and people were drowned in their, literally, I say tens of thousands, but 100,000 or more.
Unbelievable. Yeah.
So, I mean, I don't, that's what motivates me. It's not whether you bring your umbrella to work or not. It's the situations which are life-threatening. And of course, this is becoming even more important with climate change, because extreme weather is becoming more extreme and more commonplace as a result of our emissions of climate change. So actually having good advance warnings of events, of extreme events, is crucially important in helping societies to become more resilient. But having warnings means you have a week or something to move your livestock, move your possessions to higher ground, or move yourself to higher ground, whatever it is.
Yeah.
Now, the thing, however, as you say, is that weather forecasting is kind of, if you like, complicated by the fact that small uncertainties can lead to have big consequences. And this butterfly effect is sort of saying that sometimes, because to make a weather forecast, you need observations of the weather, and you feed these into a computer model, and those observations determine an initial state of today's weather everywhere around the world, and then the computer model takes that forward in time and makes a prediction for a week ahead, 2 weeks ahead, so a season ahead sometimes. And well, so the point, however, and the point I wanted to make in the book is that sometimes these uncertainties don't actually matter that much. So you can make accurate forecasts even though your initial conditions are not known precisely. But on other occasions, when the atmosphere is particularly chaotic and unpredictable, small uncertainties can have big effects.
We all know we should be lowering our carbon footprint. But what about our actual visits to a country? How do we know that our stay there causes as little environmental impact as possible, or better yet, actually improves the lives of those we buy goods and services from? Philip Brendel from Where It All Began, a destination management company for South and Southern Africa, founded the company in 2017 as the first carbon negative travel company in South Africa, focused entirely on ethical and sustainable ways of seeing the country and region. With Where It All Began, each trip is designed bespoke around your interests and needs, but all the concern of who really benefits and what positive impacts your journey can make are taken care of by Philip and his team. If you're considering visiting South or Southern Africa, get in touch with Where It All Began for a journey that will not only be memorable for you, but rewarding for the country and its people. You can follow the link in the description of this video for a 10% discount on your booking fee. Thank you for listening.
So what myself and a group of us did was develop this idea called ensemble for weather forecasting, where we run not one forecast but 50 forecasts every day, and they start from very similar initial conditions.
Yeah, there's just a diagram
Yeah,
to
you've got
show.
an illustration of this, and this was a famous storm that hit southern England in 1987, and it was famous because it was completely unforecast. Even the evening before, the television forecasters had failed to see, or the computer models, more precisely, had failed to see the storm. And what we showed by running it, this is in hindsight, 50 times, and those kind of, we call them stamp maps. They're individual kind of pressure maps, and if you can see them, some of them look. You can see kind of dark areas, which is
darker,
indicative of a very deep low pressure system. And other of the stamp maps actually have very little of an indication of a storm at all. So what this is telling you is that you can't actually make a prediction of this storm in any precise deterministic way, but the ensemble is warning you that there's a risk of something happening.
Yeah.
And the map on the right-hand side is the risk of literally hurricane strength winds, as represented as probabilities. So in the darkest area, or in the channel there, I mean, we're looking at probabilities of 30 or 40%. Along the coast of southern England, it's maybe 20, 25% or something like that. But the point is that provides a warning. Now, where this has had an impact is going back to places like Bangladesh and so on. Where this has had an impact is in an area now called anticipatory action, which humanitarian and disaster relief agencies have started to develop, where they use these ensemble forecasts to determine whether or not they will try to send food and shelter and medicine and water and so on into areas that are potentially at risk of extreme weather. And they make that decision based on whether the probabilities exceed a prior determined threshold. So they might take some value like 70% or something and say, okay, if the probabilities exceed that, then it's worth, on a kind of cost-benefit analysis, it's worth to take anticipatory or precautionary action ahead of time. And this has really transformed the way in which disaster relief works. In the old days, they would just wait for an event to happen and then go in. Of course, often all the communications are down and people are in bad state. So this is a really big improvement. So this is an area where having quantified objective probabilities has proven quite useful. And this is, so this is an area where the butterfly effect, if you like, which might seem to be a bit of a negative thing, actually has kind of transformed the way in which operational activities work, because they can target their resources onto the events which are both extreme and where there is some confidence. One can have confidence in the predictions. In my book, I showed examples, for example, of hurricane tracks, the same sort of thing. I mean, I showed an example of a very extreme tropical cyclone which hit Bangladesh, which was very, one could be confident in the prediction a week ahead.
Yeah.
On the other hand, the famous Hurricane Katrina, was an example of one which a week ahead, actually, there was a lot of uncertainty about whether it would go to New Orleans or track up the coast of Florida or where. And then it's harder. Yeah, it's harder to see. It's harder then to target sort of precaution. I mean, you would have to tell people, obviously, all the way along the Gulf of Mexico and up into Florida and so on, with that middle example of Katrina, that there is a risk, and you should think about being aware there is a risk of a very intense storm. But then you have to wait till like 3 or 4 days before you can become more certain and then start to evacuate specific regions. But the top one, which is a cyclone called Cider, was actually a week ahead, fairly well predicted. Confident one could be fairly confident that it would hit up towards Bangladesh, and so then they could take more definite precautionary measures, like where to move livestock, where to move individuals from low-lying regions. Yep.
Fascinating. And of course, it is. In your book, you speak about ensemble models being used as well, being worked on to hopefully predict global warming in the future.
Yes.
And so there's this will hopefully, depending on the outcome, put to rest a lot of debate questions. And it's such a debated and politicized issue right now as well.
Yes.
A lot of people are still asking, is it even real? Are we seriously in trouble? There's
an important point here, which can be made by an analogy with a weather forecast, if you like. I mean, if I was to tell you that, this afternoon or something, there was a 20% chance of a thunderstorm and a really, heavy rainfall or something like that, and you were planning to go for a walk in the countryside, you have a very simple decision. Do you bring a kind of rainproof coat with you, or leave it behind? I mean, if you bring it, it's a bit of extra weight. It's a bit of a nuisance. But on the other hand, if you were to get completely soaked, you'd be very uncomfortable if it was halfway around the walk. So that's a trivial example, but the point I'm trying to make with this example is that what the meteorologist does do is make that prediction that there's a 20% chance. That's kind of the best that can be done given the uncertainties and the degree of chaos in the system and so forth. And then it's up to the individual to translate that into a decision about whether to do something or not. Now, the point about climate change is, in some sense, it's exactly the same problem, but obviously magnified to a much more important extent. And the figure that you show here is one that I constructed actually from the last two of the so-called IPCC climate assessment reports. And what it shows is a kind of probability distribution of how much global warming there would be if you were to double the amount of carbon dioxide in the atmosphere from its pre-industrial level. And you can see the numbers kind of go from 2 degrees up to 6 degrees. So there are a finite number of models. So the dashed line is a sort of estimate of a kind of more continuous probability distribution if you had sort of like an infinite number of models. Now we're already over 1 degree. So doubling, we're obviously it's never going to be less than 1 degree because we're already at 1 degree. It's sort of unlikely to be 2 degrees, but it could be. But in a way, it's, you can see at levels of 4 degrees or more, it's not negligibly small. I mean, it's not, the most likely value is perhaps around 3 degrees, but once you get to 4, 5, 6, the probabilities are not zero. Now, we can kind of discuss, what this means in terms of climate, but nobody that knows anything about the climate system would deny that if the world warmed by 4 degrees or more, it would be pretty damn catastrophic for humanity. I mean, large parts of the world would be completely uninhabitable because of heat waves and so on. The sea level rise would knock out most of the major cities around the world. So there'd be kind of mass migration polewards, which basically means towards the North Pole. All sorts of potential for conflict and stuff like that. So, but then the question is, okay, I can't, that probability distribution is not something, it's not like one value, it's a range of possible values. So it's not a scientific question. You could say, okay, so do we want to make sure by taking action to reduce our emissions, we want to make sure it's never that possibility of having more than 4 degrees just never happens. That, in a way, that's not a science question. That's exactly the same question, but obviously multiplied by a trillion, to the question about whether you should pack your waterproofs before going for a walk in the afternoon. It kind of involves value judgments, because, well, we're seeing this. I mean, decarbonizing our energy system is not trivial. It's not completely cost-free. And the transition, involves disruption, which is a problem. And in particular, we want to see the whole world kind of taken out of poverty and people around the world leading, decent lives and having the same standards of living that we have in the West. And disrupting that process, is not, could set them back. I don't know. Anyway, all I'm trying to say is there are lots of issues in going from the science to the policy, and I think it's important when we have these debates with, let's say, climate deniers, that we do try to separate out the science from the policy. And the science, as represented in that probability distribution of global mean temperatures rising from a doubling of CO2, I mean, that's basically what the science says. So that's fairly, undoubtable. That's the word I'm trying to find here is, that is a fact. That's what the science is. Now, how we go from there, of course, involves things going beyond science. So I just want to make that point, whether it's weather forecasting or climate forecasting, there's a kind of scientific aspect to the problem, and there's a kind of value judgment, political, if you like to call it that, but it's something that involves value judgments, which are kind of beyond the extent of science.
So that could be if let's say the decision makers in key powerful countries were to make the wrong decision, then we might indeed see a rise in temperature. Is that am I right in saying that?
Well,
because
if we do nothing about cutting emissions, then we will unquestionably see a further rise in temperature. I mean, there's no, you have to be completely nuts not to see that.
Yeah. So people need to make.
The question is, what I can't tell you is that rise going to be a very, such a large amount that it would be utterly catastrophic for humanity, or is it an amount that, we could, with some investment, adapt to? And the problem is, because it's that distribution, that probability distribution is not like sharply peaked at one value. It means that both of those are potential future scenarios. And so the question really for politicians is whether that risk that the world will warm by what are clearly catastrophic values, 3, 4, 5, 6 degrees, are they worth trying to avoid pretty much at all costs?
Mhm.
And I think the consensus is that, that it's such a serious problem for future
Yeah.
generations that it is worth trying to take that risk.
Yeah.
It's no different, by the way, to COVID. And in fact, I had a chapter in the book about COVID prediction. But again,
Yes.
there the issue was, it's all very well, people looking in hindsight with what happened. But the problem that the politicians had to face at the time was, is there a risk that all of the hospitals will be completely overrun with COVID cases, that the whole, like the society will kind of cease to function properly. I mean, it's a
Mhm.
pretty ghastly scenario. And they judged based on the, epidemiological models. And again, ensembles of these models we used. They judged that the risk was sufficiently large. I mean,
Mm.
it wasn't certain, obviously, but it was sufficiently large that it was worth trying to take action, in this case, lockdowns and things like that, to prevent that worst case scenario. So, it's exactly the same with climate change. There is a plausible worst case scenario that is completely disastrous for humanity. And
Mhm.
the question is, given our economic status and our scientific technological status, is it worth trying to
Mm.
cut our emissions to make sure that kind of risk doesn't materialize?
I think it's, perhaps people also don't really see 4 degrees. Maybe they don't also have time to sort of look into what that actually means, and that
Mm.
it's actually quite serious.
Yes.
So a 4 degree, it's not like where you. It's not like local temperature or local weather where it's 4 degrees warmer in your city on that day. It's a global mean temperature.
Exactly.
And so I just wanted to read out just a quote from Mark Linus's book, which you
Mm.
refer to in the book,
Yeah.
6 degrees of Our Final Warning, 6 degrees of Climate Emergency. So this
Mm.
is what a 4 degree warmer world would be like.
Mm.
At 4 degrees, a whole new process has begun to unfold, making substantial areas of the planet biologically uninhabitable for humans.
Mm.
While the increased mortality risk in today's heat waves tends to be among older, very young, and other vulnerable people, temperatures at 4 degrees of global heating are high enough to reach a critical threshold that will kill anyone, however fit and healthy, because of the laws of thermodynamics. So,
Yeah, what he's referring to there, it's worth sort of stressing it, by the way, that
yeah.
the temperature is actually not the only factor in these kind of heat waves. It's the fact that as the Earth warms, it also becomes more humid,
Mm,
and these kind of deadly heat waves, where anyone, even if they're fit, will die, um, happen when the body can no longer lose heat by sweating. So, we're all
gosh.
kind of used to air temperatures being warmer than body temperatures, but the body can cope with that by sweating. We lose we cool down by evaporating moisture into the atmosphere. But
Mm,
if it starts to become so hot and in combination so humid that you can't sweat anymore, then
mm,
there is no mechanism to lose heat, and that's ultimately where you can't survive. It's as simple as that. I mean, the
yeah.
body can only operate within a certain range of temperatures. So when it
Yeah.
exceeds that and you can't sweat, then you've had it.
Gosh, well, I hope we all do everything we can
Yes.
to avoid this. Um, so, can you explain how exactly does the ensemble method work for global warming? You mentioned various scenarios. I think I understood it to be kind of like where you place a grid, a grid model all over the globe, and
Yeah.
each square represents data, and in that data you've taken as much information into consideration. Maybe you could just talk a little bit about that.
Well, what we're talking about here are actually the models, the computer models, and in this respect, a weather forecast model and a climate model are pretty much the same thing. So whether you're trying
Mhm.
to, you know, forecast what the precise weather will be in a week's time, or how, how warm and humid or how rainy or something it'll be in 100 years' time if we continue to emit carbon dioxide. Pretty much the same models are used, and the models are based on the laws of physics. So that's actually an important point. They're not kind of people like guessing what or putting in empirical rules and things. They're based, as best we can, at least, on the laws of physics. And the way the laws of physics are expressed is in terms of a mathematical technique which Isaac Newton came up with a few hundred years ago called the calculus, which talks about the rate of change of things with time, or the rate of change of, how things change if you move from one place to another. But computers can't directly solve these equations. They're too well. Actually, I mean, the equations themselves are simple, but they're difficult to solve, and they can't be directly solved. So you have to solve them by trying to sort of approximate the true atmosphere.
Mhm.
The problem is, I mean, you look at a satellite, for example, image of the Earth, and you see these big whirls, like low pressure systems, and they have scales of thousands of kilometers. But inside a low pressure system, there'll be, individual clouds which might have scales of a few kilometers. And within the clouds, there are subcloud turbulence. And the turbulence goes down to scales of centimeters, even millimeters.
Mhm.
So you have a phenomenally large range of complexity. It's all represented by these mathematical laws, but because of this range of complexity, it's too much for a computer kind of to deal with. So what you do is you have to approximate the atmosphere by imagining it's kind of big, we call them grid boxes, but there's essentially, we kind of divide the atmosphere up into chunks of, a climate model, maybe 100 kilometers by 100 kilometers in the horizontal, maybe a kilometer or something in the vertical. And the computer model assumes that chunk of air inside a grid box is completely uniform. So there are no whirls and eddies inside the grid box. Now, that's an approximation. That's not, in reality, there are whirls and eddies inside 100-kilometer grid boxes, but the model assumes that there aren't. And that's what makes it tractable. But because it's an approximation, you have to, if you were just to run your climate model, or indeed your weather forecast model, once, the fact you are making these approximations could invalidate the forecast, and it's one of the things that makes the forecast go wrong. So the ensemble method is to try to represent the uncertainty when you make that approximation. And one way of doing it, which I talk about in the book, by the way, is adding noise to the models. You make the models kind of noisy. And I'm a great believer that noise is not the nuisance that we often think it to be. It can be very beneficial in many respects, and in nonlinear systems, it can be very beneficial. So the ensembles basically give us different kind of realizations of the real world. They're each have these different noise levels of noise and things. But the range of outcomes gives us a kind of a error bar, or a uncertainty range on the forecast. And I say that could be a 10-day weather forecast, or it could be a 100-year climate forecast.
Yeah. Wow. So this is where chaos is actually the missing ingredient in predicting these very complex nonlinear systems. And so just to read the quote from Richard P. Feynman, we need to teach how doubt is not to be feared but welcomed. It's okay to say, I don't know. And so that it's interesting that becomes a key part of predicting more accurately.
Yeah, no, I think that's a super important point. And it's very easy I mean, I find this myself sometimes when you're being interviewed, like now, to kind of be more certain than you are. And often, I'm not saying you're doing this, but often journalists try to kind of push you into a corner where they're trying to make you say things that are actually
Yeah.
much more certain than you're comfortable with. And
Yeah.
ultimately, that doesn't help anyone. I mean, it might help make a
Mm.
better news story for tomorrow, but in the big
Mm.
scheme of things, it doesn't help things.
Yeah.
So yeah, I think it's
Absolutely.
important. And that's why I say, with climate change, we need to separate out the science and the politics. And often the two things are conflated together. So,
Mm.
people end up making statements about the science that are actually much more certain than
Mm-hmm.
correct.
Mm-hmm.
Trying to sort of defend a particular position. Well, it doesn't need to be defended like that. I mean, the way as I say, I see it, in my personal view, and I said this in the book, in my personal view, these risks of, catastrophic levels of climate change, which are not certain by any stretch of the imagination, but
No.
are certainly plausible,
Plausible.
are big enough that it's almost a no-brainer that we have to take some kind of
Absolutely.
precautionary action to stop that happening. Now,
Uh,
certainly in 100 years,
yeah.
I mean, we don't know exactly what it's going to work out. I mean, with a probability, you never know for sure what's going to happen.
Mm.
And I mean, it could be in 100 years, we actually find out that the climate system wasn't that going to be that catastrophically changed. I mean, it's not inconceivable,
Mm.
but it would be wrong to say, in 100 years' time, oh, they made the wrong decision. No,
Mm-hmm.
based on the evidence that they had,
Yeah.
based on all the very best science and so on, and taking account of the uncertainties and so on, actually, they made the logical and rational decision. And that's all we
Absolutely.
can do. That's why I
So,
feel about COVID. People sometimes say to me about COVID, oh, well, maybe it was an overreaction. Well, no, at the time, that was the right reaction, given the potential for completely overwhelming hospitals and so on with COVID
mm,
patients. That was the right decision, I think.
yeah, absolutely, it was. And so was, I believe, getting the vaccines.
Yeah.
Yeah, of
Yes.
course. Um, so I just want to go back to this wonderful picture on the cover of your book.
Yeah.
It's the famous geometric representation of chaos. It's
Yes.
called the strange attractor or the Lorentz
Yes.
attractor.
Yes.
How does this link into this discussion?
Well, yeah. I mean, it's something that I, as a mathematical physicist, I find extremely appealing. And I sometimes, when I give talks about this, um, I draw the well. So this is a picture or representation of a geometry that
Mhm.
would have been completely alien to Isaac Newton, and I'll explain what I mean by that in a minute. But as I mentioned earlier, the equations that or the mathematical technique we use to represent, a range of equations in physics is the calculus, which Newton, Newton and Leibniz, I guess, co-discovered. Um, so this is a picture of a kind of geometry that's generated by three equations which use the calculus, which were discovered by Ed Lorenz, who was a meteorologist at MIT in Boston. And if one had shown these equations to Newton, he would have actually understood them. He would have said, "Oh yeah, these are three nonlinear coupled ordinary differential equations." That's the sort of technical phrase for them. So
Mhm.
so Newton would have actually understood them, but for Newton, geometry was about spheres and ellipsoids and things which Euclid back from the sort of ancient Greek times would have developed. In fact, well, actually, even I, as a child, would have studied Euclidean geometry at a very early age. I'm not sure it's done so much these days, but but Euclid's geometry held fast in the sphere of mathematics for many centuries. But this geometry is the completely opposite of Euclidean geometry, and it's an example of something that's called a fractal geometry. It's a little bit hard to see that fractal nature from that picture, but basically, Euclidean geometry, if you imagine a sphere, if you imagine a sphere or a circle, and you zoom into a circle, it just gets boring. It gets, it just end up like, if you zoom in enough, it looks
like a line.
Yeah, like a line.
Just a line.
But this fractal, this is an example of a kind of a fractal. The full fractal, if you like, is the one on the the bottom right. If you zoom into it, it kind of the shape keeps repeating itself over and over. So it's complete opposite of Euclidean geometry. And the Lorentz attractor, actually it's not obvious, but it can be shown that this Lorentz attractor, if you kind of zoom into it enough, you still see structure that just will never go away. And what I do in the book is actually make a link between this geometry of this fractal attractor and some of the really deep theorems of 20th century mathematics. There's a thing called Gödel's theorem, which is about the incompleteness of mathematics. And even, the most celebrated result of 20th century maths, which is called Fermat's last theorem, proven by an Oxford colleague of mine, Andrew Wiles, makes use of a kind of mathematics that builds on this type of fractal geometry, things called p-adic numbers, which are basically fractal type numbers. So Lorenz's work, in a very real sense, although that wasn't his motivation, but it turned out that his work provides some fascinating links between the sort of classical mathematics of Newton, the calculus of Newton, and this type of extremely rich fractal geometric structure, which links to a lot of these very profound ideas in mathematics of the 20th century. And the thing that fascinates me, you see, we talked right at the beginning about quantum mechanics, and I mentioned to you the problems of trying to synthesize or marry together quantum mechanics and general relativity. And I've come to the view over the years that these amazing fractal geometries could actually be give us a clue actually how to do that synthesis. So in a sort of strange way, this work on weather and climate through studying these, I think, amazing kind of structures that are generated by these equations, like Lorenz's equations, may hold the clue to, why in physics we've had so much trouble bringing these two areas of physics together. So it's kind of bringing me back again to my roots in very fundamental physics.
Yeah. So it seems that you've brought these two concepts together in these images. Maybe you could explain a little bit about them.
Well, it's a little bit going. There's a little bit of background to all this, which I don't want to go into too much detail about, because it would probably be a bit maybe tangential. But the Nobel Prize, the Nobel Physics Prize, not the very latest one, but the one from last year, was given to three experimental physicists who showed that something called Bell's inequality was violated. Now, this is an experiment that's done on quantum particles, like photons, or could be done on electrons. In practice, they tend to be done on photons, little particles of light. And you can create two particles that are what are called entangled, they're produced by a source, and the two particles kind of move apart from one another in opposite directions. And then these experimenters, who are normally called Alice and Bob, they measure some aspect of the particle. So it's typically like the polarization or the spin, or what's called the spin of the particle, the polarization. SG is just a word for what's called Stern-Gerlach, which is a type of experimental apparatus that can measure the spin of one of these particles. If it comes out the top, then it's spin up, and if it comes out the bottom, it's spin down. And they're orientated in certain ways. Now, what you then can do is measure the correlation. So you do a large number of these, you measure the spins of a large number of these entangled particles, and you count, for each one that went out of Bob's top channel, how many went out of Alice's top channel, and how many that went out of Alice, say Bob's top channel, went out of Alice's bottom channel or down channel. So you form these correlations, and then you orientate the apparatuses in different ways, with different sub-ensembles of particles. And so you generate these correlations for different orientations of the measuring apparatuses.
Okay.
And it turns out that what Bell showed was that if you had any kind of what I would call, or what people would call sensible, perhaps that's not the right word to use. I mean, the word technically is classical, but a model that you would think would be intuitive to explain, for example, that a particle had, a predetermined value of its spin, and that it would reveal for each orientation, it would have a predetermined value of its spin. If you had a model like that, then the correlations have to satisfy a thing called Bell's inequality. And it turns out that this Nobel Prize was given for 3 experimentalists who showed quite, unequivocally that this inequality is violated for certain choices of these orientations. So the question is, what does that mean? What does this violation mean? And the conventional kind of physics explanation of this violation of Bell's inequality is that either physics is somehow indeterministic, there's something kind of random about the world that's going on that can't be described by laws, or perhaps even worse, that there's something what's called non-local going on. Now, what non-local means in this context is that the decision that Bob made in orientating his apparatus. So he's in principle, Alice and Bob could be on other sides of the galaxy. They could be zillions of miles apart. But non-locality means that Bob, how Bob chooses to set his apparatus affects the actual experimental results that Alice gets. And that's kind of bizarre as well. It would be okay if they were like a few meters apart, but when they're a few million light years apart, it doesn't make any sense.
Is that what Einstein referred to as spooky action at a distance?
Absolutely. So the first idea, which is indeterminism, he said he didn't like that because he said God doesn't play dice. By God, he didn't really mean God in the sort of supernatural creator sense. It just means physics. It doesn't make sense to think of physics as indeterministic. There must be rules. There must be well-defined rules.
There must be some reasonable explanation for it.
And and as you say, this non-locality he just described as spooky action at a distance, which again kind of doesn't make sense. But nevertheless, most commentators, particularly after the Nobel Prize was announced just over a year ago, basically said that Einstein was wrong. The world is either spooky or indeterministic, one or the other.
Or the universe isn't real.
Right, the world isn't real. So I've been kind of on a mission trying to persuade my colleagues that actually there is a third alternative, which is not well understood, which actually brings in this notion of the geometry of these chaotic attractors, And it's actually better if you go back to the cover of the book. I don't know if
Yeah.
you can. Yeah, that's a better, because it turns out, and this is where these fractals kind of come in. You see, that figure is actually just been drawn by a computer, so it's only an approximation to the actual thing. And you can kind of see there are little gaps. There are regions where it's black, and it turns out that even when you've got the full unexpurgated version of this attractor, there are always going to be gaps in it everywhere. And the more you can zoom in as much as you like, and you'll see gaps. And the gaps will get smaller and smaller. Now, what these gaps, the point about these gaps is that if we imagine the world, the whole universe is evolving in on a geometry that's a bit like this, then and we imagine. I mean, let's imagine, for example, you get up in the morning, and you let's say, I'm not sure what you do, but suppose you drive down to the to the train station, and you've just missed the train, and because you've just missed the train, you get to work late, and because you get to work late, you miss making the business deal of the century that would have promoted you to catastrophic, or not catastrophic, to supersonic heights in your career and things like that. So ever more you say, oh, if only I'd left home a bit earlier, I wouldn't have missed the train, and I would have made the deal, and my life would be so much better. But there's a kind of a question mark here, which is that, can we be sure that hypothetical world where you left your house like 20 seconds earlier, can you be sure that world is consistent with the laws of physics? And in particular, if you were able to do it, and I mean, that will depend on the detailed laws of physics, but if it turned out that hypothetical world, and it is hypothetical, it's what they call counterfactual, because you actually left your house at 7:45 precisely. So that's the fact of the matter. So the world where you left the house 30 seconds earlier is a counterfactual world. Now, if that counterfactual world, when you plotted it in this way, turns out to lie in one of these gaps in the fractal attractor, then that's telling you that world is inconsistent with the laws of physics. So in a way, you shouldn't beat yourself up for not having left your house 30 seconds earlier, because it would have been impossible to do that, because it would have contradicted the laws of physics. Now, these same types of counterfactual kind of worlds, if you like, also occur in Bell's theory, in the improving the Bell inequality. In other words, what you have to assume to derive Bell's inequality, the thing that the 3 Nobel Prize winners proved was violated experimentally.
Right.
But what you have to assume is that hypothetical worlds where Alice and Bob measured their particles in a different orientation to the ones that they actually measured them, you have to assume that those hypothetical counterfactual worlds are consistent with the laws of physics. And what I'm saying basically is that if the world is evolving on one of these kind of fractal geometries, then it may well, not only that, I'm claiming it is the case that these counterfactual worlds where Alice and Bob measured differently to how they actually measured turn out to be inconsistent with the laws of physics. So in other words, just putting it all together, these kind of fractal geometry, this fractal geometry gives you a reason, or if you like, or a mechanism. I don't know for sure whether this is the right way forward, but I think it's plausible that it is. But it gives you a reason to think that the Nobel Prize does not actually prove that Einstein was wrong
Yeah.
to believe that God doesn't play dice and that there is
Yeah.
no distance. It gives you a way out, which is typically not being pursued very much by contemporary physicists, but I believe is something that I'm hopeful more attention will be given to in the future.
I must say it's quite a complex subject to grasp, because it seems to sound like, on the one hand, you have reality, or the world or a situation that is consistent with the laws of physics, and then a hypothetical situation that isn't, or can be, or just isn't.
Well, so yeah, you're right to say it is not. I mean, it is it's not easy to get your head around it in a straightforward way. But what I'm saying is, let's say there are two options available to you. Well, let's say, when you actually get out of bed, you have two options. One is to leave your house at 7:45, and the other option is to leave 30 seconds earlier than 7:45. At the time you get out of bed, both may actually be, well, both. I would say that both of them actually are at that stage consistent with the laws of physics. But what happens is, once you have made that decision to leave at 7:45, and you actually have left at 7:45, then the other one becomes counterfactual. Up until that moment when you actually left, it's not counterfactual, it's just a possible, occurrence. But once you've actually left at 7:45, then that other option is counterfactual. It cannot have occurred because you actually left at 7:45.
Right.
And it's that condition that you actually left at 7:45 that makes the other option, the counterfactual option, inconsistent with the laws of physics. It's knowing that you actually left at 7:45 that makes the other. So that's the kind of, if you like, that's the subtle thing about it. I'm not saying it's easy to kind of grasp exactly, but
is it at all? I mean, when you gave the example of the invariant, I think it's the invariant set, but that it almost seems like the counterfactual and the real world, or the world that conforms to the laws of physics, seem to be evolving together. Maybe that is the analogy, or that is a concept that could be represented as, in the same way that the weather is forecasted, because there are any number of possibilities that exist, but that might not happen, but that still pose a possible threat. And you give the example of Michael Fish, look, considering the fact that the methods used back then were not as accurate as today. However, in order to get more accurate predictions, it is really important to take into consideration what we think is not possible.
Yes, look, I mean, you can, if again looking at that figure, there are lots of these lines that are bunched together, and they you can kind of see it a little bit if you take the word T of doubt, the last letter, and imagine a little kind of circle around the top edge of that letter T, and it'll capture a bunch of those trajectories. And you can see, as you go through the letter M of primacy, they start to spread out. And in terms of weather forecasting, some of those lines might correspond to severe weather events, and other lines might correspond to kind of fairly innocuous weather events. But when you actually measure the weather, so when the initial conditions are, near the top right of that letter T of doubt, you don't know exactly, the observations are never precise enough to know for sure. So what you do is you have a little little region, if you like, of the attractor, which encompasses many of those trajectories. And well, in the ensemble forecasting, we run 50 of them, and maybe 20 of them will give hurricane force winds and 30 of them won't, and that'll give you a probability. Now, so that's why doing and you're right to say, in a sense, once you know the weather that happens, so if you go forwards a week or something, and then what the weather, and let's say it was very extreme weather, then you can say all those whatever it was, 30 trajectories that didn't produce extreme
That
weather.
didn't happen.
They were counterfactual trajectories, so
Yeah.
they correspond to weather that didn't happen, but might have happened.
Could have happened if.
Could have happened. But what I'm saying is,
Yeah.
when it comes to this much more subtle and difficult problem of Bell's theorem, you have to recognize that in that small region at the initial time where we had these, let's say, 50 trajectories, there are gaps. There are always going to be gaps. And the gaps really are corresponding to hypothetical worlds, which would be inconsistent with your laws. If your laws say that the real world is evolving on one of these fractal attractors, or I use the word invariant set because they're invariant. If you're on it now, you're on it forever, and if you're not on it now, you're never ever going to be on it.
Is this kind of a representation? Yeah.
But the point about the Bell's theorem is that it does make use of counterfactuals, which with the model that I'm using, these counterfactuals really, really, really do lie in the gaps. They're not states that correspond. So I'm not trying to make the point here, although I know I've simplified it a little bit. I'm not trying to make the point that every counterfactual that you can think of is necessarily inconsistent with the laws of physics. But conversely, you can't assume that every counterfactual that you can conceive of is consistent with the laws of physics. And I'm claiming that in Bell's theorem, you do actually, or you can devise a model where the counterfactuals that you need to consider to prove the Bell inequality are inconsistent with the laws of physics.
Wow.
The idea here is that in A, we're looking at what's called a trajectory in state space. So how the system evolves in its state, the space of states. So the Lorentz attractor is evolving in the space of states of the Lorentz model. And the fractal structure that I'm kind of proposing here is actually a little bit like a piece of rope that if you apply a magnifying glass to that line, it actually looks like a kind of you have a helix of strands, and then you zoom into that helix and you find that helix is made of a helix, and similarly you zoom into that helix and it's made of a helix of a helix. So you have this kind of nested fractal structure. If you were to take a cross section through that piece of rope, you'd see these kind of multiple strands, and this is exactly what mathematicians often use when they're describing these p-adic numbers, which I mentioned briefly as a type of number system that are used by people like Andrew Wiles for proving number theory problems like Fermat's last theorem. And then C is showing, the case when a quantum system can interact with the environment and it just spreads out. It's a process called decoherence. So you lose this kind of helical fractal structure. And D is just and that is what goes on when you try to measure quantum systems. I don't want to go into this because it's probably too complicated, and I think we're running out of time anyway.
All right.
But that's the basic idea.
Okay, so just right. Yeah. So I think it's just a quote from your book that I'm going to read here. In invariant set theory, by contrast, real and counterfactual trajectories have a distinct but interdependent ontology. They are not the same, but equally one cannot ignore the counterfactual trajectories if one wants to understand evolution on the real trajectory. And so I think it's interesting how that ties together, the understanding of predictions with chaos. And then you go on to say counterfactual trajectories are in fact real trajectories, but for earlier or later epochs of the universe. Hence, according to the invariant set theory, quantum physics ties together real-world evolutions of multiple different epochs of the universe. Not only is the spatial universe undivided, but so too are the epochs of the universe. So it's, I think you're referring to thinking big, and being able to zoom out and think about concepts like the undivided universe. Maybe you can talk a bit about that.
Well, one thing I say in the book, if people read it, which I'm kind of keen to just stress here, there are three parts to the book. In the first part, I talk about some of the conceptual ideas, behind chaos theory, behind these fractal attractors, and so on. And that is, I would say 99% hard, firm science. Mathematics. It's stuff that there's little room for disagreement about. I mean, some of it can be a bit conceptually challenging. I understand that, but on the other hand, it is fairly well sort of settled. The second part of the book is about, it focuses on some of the applications of chaos theory, and stuff that I've worked in weather and climate forecasting are, I would say, fairly well established now. I talk a bit about the application of ensembles to things like COVID and epidemiological forecasting, and also to economic forecasting, where I think there's a lot of scope for these ideas to blossom, and even
Absolutely.
conflict forecasting, which I would say is still at a very early stage.
Yeah.
But it's kind of science that's either well established or is not far from being well established. But in
Right.
the third part of the book, and now when you're talking about some of these quotes of counterfactuals, I do try to, if you like, warn the reader that we're straying into area which is definitely speculative, and where the science isn't settled. So I'm not trying to be. I can't really be too dogmatic about anything that I say.
Okay.
It's very uncertain, I would say. So
It's uncertain. Yeah.
but I do, if one takes the view that the universe is evolving on one of these fractal sets, then what are the implications of that? And I think one of the implications is that the universe probably does go through these multiple cycles of Big Bang to Big Crunch to Big Bang to Big Crunch. I know there are lots of observations which at first sight may not be, like dark energy and things, which might not be consistent with that idea. But I try to discuss this a bit in the book.
Yeah.
But if that's right, then as I say, what we perceive today to be a counterfactual world, close to our own world, would actually be the kind of reality that we perceive in a future epoch. And I find that idea, by the way, rather philosophically appealing, because we often wonder about afterlives and meeting loved ones again, and here's an opportunity for that to happen in a perfectly natural way, if you like. And it's an opportunity, if you like, for us to not make the same mistakes that we made this time round. But equally, things that we got right this time round, we may get wrong the next time round. So who knows?
Yeah. It's very it's fascinating. I think it's the first time when well, not the first time, but perhaps any genuine, real applicability of this concept actually comes into play. And of course, it's not. It requires so much more study and research. But you also bring up a CERN for climate change in in the book, and it seems that would be necessary to actually provide the computing power that is able to process this kind of information. And that this would actually bring together all of your theories in a real in a concrete way. And how would that, how would that sort of link CERN for climate change and using Zeta computers, it seems to all link together. What exactly do Zeta scale computers do? How do they process all this information? Quantum computing is quite complex to understand.
Well, the concept of a CERN for climate change is very much geared at a very practical level, which is that, we talked about earlier this idea of, dividing the atmosphere up into chunks called grid boxes.
Yeah.
And, in what we would like to do is to reduce the size of these grid boxes down to, sizes that are as small as possible.
Mm-hmm.
But the problem is that, reducing the size of the grid box increases the computer cost. And
Right.
computers are, supercomputers are expensive. So we're in the era of what's called exascale. So that means like a billion calculations a second, which is an amazing number.
Yeah.
And it's not just me. A group of us believe that we can make some big progress in climate modeling, particularly at the regional scale.
Yeah.
Um,
I
with
just
these computers. But the problem is that it's not something individual countries can afford. I mean, individual countries may have exascale computers, but they're typically used for a range of different applications. So, yeah, range of applications, including astronomy and modeling the universe and things. But we're
Mhm.
claiming that we need this dedicated to the climate problem if we're really going to improve our predictions.
Yeah.
And the best way to do this is actually to do it internationally, pool, because it's a global problem manifestly. So trying to pool human resources, computational resources, financial resources
Mhm.
would probably be the best way forward. So
Yeah.
we'll see what happens.
Yeah, it's an interesting quote that you made in your book, that reductionism is a flawed philosophy, and that if we are forever going to be smashing particles to find the smaller and smaller and smaller particle, it does sort of almost become totally impractical. And that you say that there are better ways than creating bigger and bigger hadron colliders.
Right. Well, we're jumping. We jump. I mean, the problem with, as you rightly said at the beginning, the problem with the book is it's extremely wide ranging, and
Yeah,
the CERN for climate change, is tackling a practical problem about how to
yeah,
forecast, you know, uh, for countries like, Pakistan, for example. Last summer, Pakistan had some pretty devastating floods.
yeah,
Question is, in the next 50 years, how frequently will those types of floods occur, or actually is drought the more pressing problem for that sort of part of the world? So that's tackling a very practical problem. What you're talking about here is something much more at the sort of more sort of fundamental philosophical end of physics and
hmm,
so on. And I guess what I'm trying to say here is that, we talked about these fractal attractors
hmm,
being kind of important, or providing important clues for how physics works at the quantum end. So, we talked about Bell's theorem, for example.
yeah,
Um, Now these fractal geometries are very kind of what I would call holistic structures. They are, you could see those kind of it looks like a big butterfly or something like that in a sort of simple way. It's got these strange wings, but it's very fractal structured. You know, the idea would be that structure, I mean, if this idea is right, it means that we have to think about the structure of the universe on the very, very largest scales, if we're to understand properly how the world works on the smallest scales. So the quantum scale is typically a very small scale. But what I'm arguing with these fractal geometries and the gaps and so on in the fractals is that it's the kind of structure of the universe on the very large scale, which is going to be crucial in understanding how the world works on the small scale. And that's why I'm saying it's kind of 180 degrees in the opposite direction to what most kind of conventional physics thinking has, which is to say, to get to understand better, you can understand why this is, because it goes back to whenever it was 1600s when the microscope was discovered. People say, oh yeah, we look at stuff under a microscope, we can see that biological stuff is made of cells. And then, cells, you look a bit more, and cells are made of nuclei, and the nuclei, have molecules, complicated molecules. The molecules are made of atoms. The atoms are made of electrons and protons and neutrons and so on. So, we have a history in science of the more we chop things up into smaller things, it looks like we do improve our understanding. But I'm kind of saying that may not be true forever. And maybe that the kind of bottlenecks that we're having in our understanding of physics might actually be resolved by trying to bring in ideas from thinking about physics on the very largest scale, in other words, the scale of the universe, as much as these unbelievably small scales.
Yeah,
so
absolutely.
It's not reductionism. It's not reductionism in the sense, I mean, I'm not trying to say that thinking logically is a bad idea, but this idea that's smaller, sometimes people call it methodological reductionism. I don't know if that's it, or spatial reductionism or something like that. That's where things may be wrong. And by the way, anyone that has any kind of artistic sense in them, I mean, I play a lot of music with my guitar and stuff. I mean, if you analyze things from an artistic, it doesn't matter if it's a piece of music or a painting, or a piece of literature like a Shakespeare play or something. I mean, you can't make any sense understanding those pieces of art without looking at the whole structure. You'd never analyze a Beethoven symphony by just drilling down into one bar and beating to death all the sort of semiquavers that are in there. You've got to look at the whole thing, each movement, what's he trying to say, blah, blah, blah. Same with Shakespeare, same with drawings and so on. So it's kind of a concept which I think in the artistic side of the world, people, would almost shrug their shoulders and say, how could it be otherwise? But, it's not the way science has gone in the last few hundred years. And I'm kind of the opinion that, as I say, some of these very deep problems about things like the meaning of quantum physics and our inability to marry quantum physics and general relativity together, maybe that really at the deepest level, it's because we need to give up on this idea that smaller is more fundamental, and that actually our understanding is going to be only come by actually encompassing the largest scales as well as the smaller scales.
Right. Okay. So I think that pretty much brings us to the final three questions that are kind of fun questions, but that I find to be often very illuminating when asking scientists and biologists to put themselves into a subjective state. Okay. So which work of literary fiction has had the greatest impact on your life?
Yeah. I mean, you say fun question. Of course, there's a nightmare questions for me.
There's more illuminating of your.
Well, I'm going to say something a bit nerdy.
Looking at the whole.
I do read. I mean, I do read a lot of literary sort of books and things. But I have to say one sort of I did read a bit of science fiction when I was young. I don't read very much these days, but one that
I'm
I
a
always
big
remember.
sci-fi fan.
Sorry?
I'm a big sci-fi fan.
Okay. Well, when I
Yeah.
was quite young, I remember reading a book, not a book, but it was actually a short story of Isaac Asimov called Nightfall. And
Wow.
if you've got a minute, let me just because
Yeah,
it just
please do.
symbolizes absolutely everything in my kind of way of thinking. It kind of so Nightfall. It was about a planet and a civilization that lived on a planet, which instead of having one sun, it had one star, one sun. It had something like 4 or 5. I can't remember the exact number of suns that it kind of orbited around. These stars kind of you often see like binary stars when you look up at the sky. There were several of these stars, and there was a
Yeah.
planet which presumably had a very complicated orbit around these things. Anyway, it was such that pretty much all the time one of the suns was above the horizon, which meant it was almost always in daylight. But every, I don't know, every whatever 100,000 years or something, 10,000 years, whatever it is, there would just be a very rare moment where all the 4 or 5 suns were below the horizon, and they would experience darkness.
Wow.
And the astronomers had worked out that they were about to hit one of these periods of darkness, kind of any day, and they went back to the sort of the old writings, the kind of mythological writings that people had, and they found that the last time this happened, it was written down, but all they could find was that people kind of went mad. They couldn't cope with this darkness. It was kind of completely like they went bonkers, and they couldn't work out why would they go bonkers. Anyway, they tried to they put people into dark rooms and just made sure they didn't go bonkers. So it's fine. Got people to shut their eyes for like half an hour, make sure they don't go bonkers. That's all fine. So anyway, it seemed to be. We can't work out why they're going bonkers, but we seem to be prepared. Anyway, so what actually happened was that the darkness happened, and what they saw was thousands of little dots of light in the night sky, stars. And in fact, they lived, close to the center of the galaxy, so there were actually millions more stars than there were in the night sky that we see. And they suddenly, for the first time, realized that they were not alone in the universe. There are all these other places, stars and things.
Wow.
That's why they went mad, because they thought
That's incredible.
it was like an existential realization.
Crisis.
So from going from thousands of years thinking they were the only people, in the world was just, themselves. So I just thought that's a really beautiful illustration of something. This kind of symbolizes for me the best examples of how science progresses. I mean, Einstein's theory of general relativity is like that. It's something nobody would have thought of, nobody would have realized until somebody did realize it.
Wow.
And they said, "Oh my God, of course, that's what it is." And it's like see the night sky. Oh my God, of course. We live in a universe where there are lots of other stars and suns and presumably other planets and things. So things are not obvious until you see them, and then they become obvious. And that's kind of the, that's the best type of advance in science. So anyways, that had a big impact on my thinking.
I love that. I'm definitely going to go and get that book immediately. Okay. I thought this is kind of a funny question. Would you rather live in a counterfactual trajectory or a real trajectory, and why?
Well, you see that what I believe is that we will the worlds that we deem to be counterfactual today will actually realize in future epochs of the universe. So fortunately, it's not one or the other. We just have to wait long enough, if you like, and we will realize these counterfactual worlds.
And I suppose the last one is a very cheeky question. I'm sure there are many scientists and philosophers, scientific philosophers out there that would think this is a ridiculous question, but why not? If you were a particle with consciousness, what is the first thing you would do to confuse scientists trying to study you?
I really haven't thought an answer to that question. I mean, I'm not sure I believe that particles have consciousness. And if
Okay.
I was a particle with consciousness, I'd be doing everything I could to try and make us humans understand what's going on.
Okay.
But,
You could be a bad particle or a good particle that would be helpful to scientists. Or
well,
one
I
that
mean,
is just continuously
perhaps the answer
elusive.
is making things too kind of obvious would be a bad thing because, again, it's a bit like the Isaac Asimov thing. The obvious answer why they went mad was that they couldn't stand the darkness. So the society invested. I mean, I'm now extrapolating a bit from what Asimov wrote, but you could imagine they
Yeah.
would invested like millions of pounds in these dark rooms and got people to sit in there for hours at a time to kind of adjust the dark. But they completely missed the point.
Mhm.
That wasn't the
Mm.
reason. So, if I was a mischievous particle, I'd make the laws of physics too obvious, and then, I mean, Einstein said the law. What did he say? The Lord is not malicious, but subtle,
Mhm.
and the laws of physics are definitely subtle. But once we see them,
Mhm.
then it becomes clear. But this is why I don't like about things which just seem superficially too obvious, but don't have a kind of anything deep to them.
Yeah.
I could talk a bit about God, but perhaps that's not the right time to do that. But anyway.
Yeah, unfortunately, we're running out of time. But just a quick, just a few words for those looking to study in your field. What does somebody do? How does one go about it? Where do they study? How long does it take to become a mathematical physicist? There's a couple of
Uh,
questions in one.
yeah, I mean, I mean, I mean, the main thing is you've got to want to do it. I mean, I think I knew at a fairly early age that's what I wanted to do. I'm always a bit reluctant to just say, oh well, I mean, you get lots of TV programs which make science sound like it's always going to be super fun. It's always going to be super easy and everything. Well, most of the time it's not that easy,
Yeah.
and in some sense, and most of the time, it's not even that much fun because you're having to if you do let's say you do a PhD. I mean, you'll be drilling down into a probably quite a small aspect of a particular problem, trying
Yeah.
to understand things in detail about it, and you've got to kind of want to do that. It can be a bit of a lonely experience sometimes because you are spending a lot of time on your own trying to really understand something in depth. And,
Mhm.
for a lot of people, that isn't for them.
Mm.
And I can understand that. But, if you definitely want to do it, then, you do an undergrad degree in maths, physics, or some kind of STEM subject. You do a master's, PhD. It is becoming more difficult, unfortunately, with careers in academia are becoming more difficult. But, I spent a lot of my career
Yeah.
working actually in government labs doing the weather climate stuff, which I found very rewarding. I mean, as we spoke at the beginning, doing something where what you've done, will affect people's lives around the world.
Mhm.
Every time there's some extreme weather event, I mean, that is quite a kind of gratifying thing. So yeah, careers don't have to, in maths, physics don't have to be in academia alone. There's lots of interesting stuff, particularly nowadays with climate change, in all
Yeah.
sorts of non-academic areas. But the bottom line is you have to want to do it, and you have to be prepared to sort of, spend time drilling down into what could seem to be a very small part of a problem to really understand it well.
Absolutely. Well, I encourage everybody to read your book. It was really, I'm the better for it, and I'm just really, really grateful to have had you on the show. And thank you so much for your wonderful insight and your new and fresh perspective on some classic problems in physics.
It's very
Well,
kind
thank
of you.
you.
If I could just say very briefly, my family persuaded me, I have to say it was quite tougher than I thought, to read the book out as an audiobook. So if you want to hear the author, as it were, speaking, you can get it as an audiobook as well.
Absolutely. So it would be available on, I suppose, audiobooks, and I downloaded mine from Amazon, and of course you can get it in any good bookstore. So, well, thank you so very, very much. And yeah, good luck with everything, and I wish you all the best.
Thank you very much indeed, Victoria. Thank you.
Thanks, Tim.